In this presentation, we're going to continue our conversation about electrical and talk about meters and meter usage. Most technicians have the meter as the first tool out of their tool bag and the last tool they put away. It's very important that you read the manuals and understand all the functions that come with your meters because these change from time to time. Every model is a little bit different, so what we talk about in this lesson may not match your meter exactly. So it's one of the tools, since you're putting it in high voltage, since you're using it all the time, take the time and read the manual. We have two basic types of meters. We have the old style analog meter and we have the digital meter. The analog meters have been around for years. They've been the workforce of the HVAC industry. They're extremely sensitive though, and they don't stand up well to being tossed around a truck. They're used today when technicians are looking for extremely accurate measurements. Most of the time they're kept at the shop, and if you need it for some reason, you'll sign it out and take it out with you on the job and then return it. The analog meter, basically nothing digital on it. You have a pointer and on a scale, and then you have the different scales down here that you can change to, okay? In other words, if you want to read like 100 volts or 120 volts, you'll go on the 300 volt scale. If you want to read under 100 volts, you'll go either to the 30 volt scale or the 100 volt scale. Okay, the scale is basically says how sensitive is the meter going to be to electrical or resistance. Digital meters have almost completely replaced the analog ones. They stand up a lot better to being dropped. They stand up to the different temperatures. They stand up better to being tossed around a truck. That doesn't mean you should destroy the thing. That means they'll just stand up to it. Digital meters are usually accurate and they'll auto range. In other words, you don't have to change the scale. You don't have to change the range of the meter manually. Now, one note on digital meters that's sort of important. They're as good as the batteries that are in them. So as you use it, make sure you have extra batteries around because the digital meters are as good as the batteries you have in them. And this is just an example of one of the style of digital meters. You'll notice that on the knob, on the adjustment and selector switch, there's only like one voltage, millivolts, ohms, and current. Several basic electrical rules we have to talk about prior to understanding what the meter is telling us. Okay, these rules are all based on voltage, amperage, and resistance. Sometimes you'll hear technicians talk about something being in series with something else. Okay, series means in the same line as. This example, the red ball is in series with the blue ball, which is in series with the light blue ball. Okay, there's no way for, let's say if we have electrical source starting here, if we have current running, there's no way for it to get from the red ball to the second blue ball without going through the darker blue ball in the center. Parallel circuits is things are next to, okay, but never converging or diverging. In other words, it's almost like railroad tracks. There's two tracks next to each other, they did never meet. Okay, so this is the exact same principle, but with parallel circuits. Okay, if I want to apply voltage just to the blue ball, I can do so because would put my line here and neutral over there. If I want to apply voltage to just the red ball, I can do that as well. Okay, and I can leave the light blue ball totally out of the circuit, or I can apply power to all three of them at the same time. So this is an example of parallel. Then we have different switching, okay, different types of circuits. Open circuits are circuits that don't have a complete path for electricity to flow. Now, we have to think about all circuits have to have a source, a switch, a path, and a load. If any of these components has a break or is open, the current cannot complete its circuit. So again, very critical to remember, every circuit has to have a source, a switch, a path, and a load. If any of these components is missing, the circuit will not work. So this is an example of an open circuit. Okay, I have line, neutral, and then I have switch 1 and B1. But this area in here, okay, right there, that's an open in the circuit. Electricity can't flow from this side of the switch to this bulb because there's a break in that circuit. Okay, when you measure voltage across an open circuit, you'll always get a reading of source voltage. Now notice we're not throwing a number in here. The circuit could be 120 volts, could be 24 volts, but voltage across an open circuit, you'll always get source voltage. When you measure resistance across an open circuit, you always get infinite because it's infinite resistance. There's no way for power to get or from current to get from one side of that open to the other side of that open. Okay, now your meters may show it as OL as well. Now, a closed or complete circuit is the exact opposite of an open circuit. A closed or complete circuit is one that has a complete path, source, switch, and load. The load is operational in a complete circuit, and the switch is closed in a complete circuit. So we take the same circuit with our switch and light bulb. And if you remember, we had back here, we had an open in this switch. Well, right now the open isn't there. Okay, so we don't have to worry about that anymore. So the power, the current can start there, can come through the bulb or whatever this load is, do its work, and again return to neutral. So we have a complete circuit. When measuring a voltage across a closed switch in a complete circuit, you get 0 volts. There's no difference in potential. There's no power waiting at the switch, I think is the best way to put it. When measuring voltage across a full complete circuit, you'll get source. So voltage across load is identical if the load is working or if the load is bad. If you have all the switches closed and measure voltage across the load, the circuit is good. If the load is not working, then you have a bad load. If the load is working, then the voltage you read is the voltage the load is using. So again, when you take a voltage reading across a load, if you get voltage, the load is either working or not, but the circuit is good. If the load is not working, which you can see, it's a bad load. Replace the load. If the load is working and you can see it working, you're in good shape. You don't have to do anything. Current is another measurement you're going to be taking with your readers. It's amperage, okay? It will be 0 amps in an open circuit because nothing's being done. No work is being done. The electrons are not moving. In a closed circuit, the amperage you measure may change based on where you take your readings. Meters measure most often voltage, current, resistance, capacitance, frequency, and temperature. For this, we're really just worried about voltage, current, and resistance. Frequency in the United States is pretty much standard at 60 hertz, so you don't have to worry much about that one. Temperature, it uses your temperature, it uses a second temperature probe on the meter, okay, that you have to replace. You have to take the leads off and put the temperature probe on. Capacitance we'll talk about in the future, but it has to do with checking and making sure capacitors are okay. Voltage is the most frequent measurement you're going to take. Now, here's the thing. Voltage, you're going to be taking measurements dealing with live equipment. So we're not going to have the power turned off when you're taking volt readings. Sort of is counterproductive. So to measure voltage, you're going to turn your meter on and set it to volts or V, depending on what your meter shows. You're going to make sure the leads are plugged into the correct place on the meter. And you're going to put the leads in parallel with or next to the point in the circuit you're trying to measure. Hold the lead steady without touching any of the other metal with your fingers or each other. Watch the display until your meter stabilizes on a number. That is your reading. So let's say we want to take a voltage reading across this open switch, okay? And your meter is right here. This is a meter. You have 2 leads, okay, and you want to see what the voltage is across this switch. So you put 1 lead on one side of the switch, 1 lead on the other side of the switch. Your meter is now next to, it's in parallel with the switch you're trying to take a reading on. So we know voltage across an open switch is source. Well, source here is given to you, okay? So there to there is 120 volts. Voltage across an open switch is always source. Now, if I close the switch and have the same meter in the same position, voltage across a closed switch is 0 because, and we'll prove it, but this bulb is getting all. Voltage across a non-powered load is 0. Think about it, it makes sense. You don't have a way for line to get to this bulb. Okay, I have neutral on both sides of the bulb because that's what happens. So it's 0 volts. Voltage across a powered load is 120 volts. The load's doing the work. The light bulb is getting all the power in this case. Could be a motor, could be anything else. Now, if for some reason the filament in the light bulb breaks, which is what we're showing you right here, okay, right here, there's a broken filament in that bulb. So voltage, line voltage cannot get past this break. Neutral cannot get past this break. So it's acting like an open switch. So voltage across an open powered load is always source. The biggest difference, the load is not working. So between here, where the load is working, and here, where the load is not working, we have the difference. Both readings are 120 volts. The difference is the bulb is not working. Voltage across a full circuit from line to neutral, or even if this was L1, L2, L1, L3, okay, is always going to be the full voltage. In other words, if you are told or if you know the circuit is getting 120 volts, line to neutral should be 120 volts. That's probably one of the first measurements you want to make on any piece of equipment you touch. We want to make sure that you know that full source voltage is going to be there. So measuring the resistance of a circuit, we have to disconnect the circuit from a source. With resistance measurements, we can't have any power on the circuit. We need to decide what component or portion of the circuit you want to measure, and you want to disconnect the wires to or remove that part. In other words, we want to isolate the component. It's extremely important with resistance readings. You cannot have power on the circuit and that you've isolated the component you're trying to check. Set your meter to ohms. Touch one lead to the other. It should show a reading of 0 on your meter. If for some reason it does not show 0, check your leads for damage and make sure they're plugged into the right spots on your meter. Again, very important. Now touch one lead to each side of this component or isolated portion of the circuit that you're testing. Wait for a number to display and record that number. This is the resistance. Resistance is shown in ohms. Okay, so we want to take a resistance across this open switch. Let's say we want to take resistance of switch 1. So what we are going to do is we're going to disconnect L and neutral. In other words, we're going to isolate this component. And by doing that, we're basically disconnecting one side of it. I don't have to disconnect both sides of it, just one side of it. I'm going to put my meter, which is right here. I'm going to put one lead there, and I'm going to put one lead there. Now, in the grand scheme of things, this meter, because this is isolated, it's no longer in parallel. The meter is a power supply. It's going to supply voltage, and it's going to supply current, and it's going to attempt to get it through the complete circuit. But because it's open right here, the reading is going to be infinite. Resistance across an open switch is always OL, or infinite. Resistance across a closed switch is always 0 because we have a path for the electricity to flow without much of a problem, okay? So I have my meter here. It's sending voltage in because the meter is a voltage supply and resistance, and it's coming back here, and it's making this full path back to the meter. So, and there's no resistance, okay? So everything the meter is sending out is coming back. So resistance across a closed switch is always 0. Resistance across a good load is some number, okay? It's not the source, it's not 0, it's not infinite. Resistance across a good load is some number. Resistance across an open load is identical to an open switch. It's OL, or infinity. Because again, there's no path for the power to flow right there where that winding or filament or whatever is open. Measuring current or amps, determine which type of amp meter you want to use. This has to do with the amount of current in the circuit. The clamp-on meter is used for higher voltages and currents. The inline meter is used for lower voltages and currents. So to measure current with a clamp-on, okay, make sure that you close the switch to energize the circuit, put the clamp around the current, around the wire. Make sure the system's running. Clamp the meter around a single wire and wait until the number stabilizes. This is your amperage reading. Relatively easy. If the current is too low to really register, like if it's registering decimals or if it's wavering around a little bit, try using an inline meter. That's not possible. Wrap the wire around the clamp 5 to 10 times. Take your reading. Divide the number you get by the number of times the wire is wrapped around the clamp. Okay, inline meter, basically you're opening a path in the circuit, you're putting your meter in series with the rest of the circuit. Now be very, very cautious on this. Most meters don't stand up well to high voltages in this scenario. So make very sure that your amperage and your meter can handle each other. Check the manual. Okay, so if you measure in line, make sure the power to the circuit is turned off. Check with your voltmeter to verify this is the case. Disconnect a wire directly before the component that you're concerned about and put your meter in series or in line with the component to complete the circuit. Make sure the meter is set to amps and the leads are plugged into the correct spots. Turn the circuit back on, allow the display to stabilize on the meter. This is your amperage reading. Make sure that you know the levels of voltage and current your meter is rated for. Don't exceed it. Okay, if you suspect this is close, use the clamp-on method. Now, most of the time when you're going through a circuit, you really don't have one switch controlling a load. Okay, you might have safety devices, you might have multiple switches, you might have sequencing of operation that requires certain switches to be open and closed. Okay, most circuits in the HVAC industry have more than one control device. We have to find a reliable, organized method to find problems in a circuit. Okay, most good technicians start diagnosing a problem by using the Hop-scotch method to trace the circuits. It's a very simple procedure and it works every time. First, make sure your meter is set for volts and make sure the leads are correctly plugged into the appropriate places on the meter. Next, check voltage across the two endpoints of the circuit. Okay, we talked about this in an earlier slide. Your two endpoints of your circuit are line and neutral, or in some cases line and line. So we're going to take the voltage across the full circuit first. In this case, it's a 120 volt circuit, so we should get 120 from line to neutral. If you don't, the problem is not in the circuit, it's before the circuit. Okay, next put one lead onto the start point of the circuit. In this case, we're going to use L. Keep that lead there. Use the second lead to go from point to point in the circuit before and after each switching device and load, checking for problems until you find the open. Okay, so in this case, we are across the full circuit, 120 volts. I'm going to leave a lead on L, and I'm going to put a lead on the line side of switch 1. Okay, in other words, we're checking this wire between L and switch 1. Since it's a good circuit, we know we have 0 volts. As soon as that shows up, we say, okay, cool, that wire's good. Then we're going to move to the load side of switch 1. Okay, I get 120 volts. Right there, okay, this is oversimplified, but right there, the good technician knows switch 1 is open. Okay, remember, voltage and resistance across an open switch is always source. So I can verify the problem by starting from the other side of the circuit. So I go to neutral, to line, 120. Keep the lead on neutral. Go to the neutral side of B1, 0. Good, my wire between neutral and B1 is good. Go to the line side of B1. Okay, that's the side to line, 0. Okay, we know we don't have a break there. Jump across that switch, neutral to the line side of S1, I got 120 volts. Okay, we know switch 1 is open, and we verified it twice. So it's extremely important to know where your switching devices are. It's extremely important to understand the Hop-scotch method, and it's extremely important to remember voltage across an open switch is source, resistance across an open switch is OL, voltage across a closed switch is 0, and resistance across a closed switch is 0. If you know those concepts, you'll never have a problem using your meter through a circuit.